So let's learn a little bit about strong acids and bases versus weak acids and bases. We mentioned strong acids and bases before in chapter 9 when we talked about dissolving things and how some things are strong electrolytes. Strong electrolytes were ionic compounds and then also strong acids and bases. So the strong bases that we have are all hydroxide containing bases, hydroxide salts of the group 1 metals, and then the group 2 metals, as far as they dissolve, calcium and strontium hydroxide are not completely, they don't have a very high solubility, but the compound that does dissolve completely dissociates into ions. So these are all hydroxide containing bases, and then strong acids include the acids of many of the halogens, and then also sulfuric, nitric, and perchloric. So if you have a strong acid, then that means anything that you put into solution will separate into ions. So if we take some hydrogen bromide gas, we put it into water, it will completely dissociate into hydrogen ions and bromide ions. So let's say we have 0.34 moles of hydrogen bromide and none of each of these. Then pretty quickly, whenever it's dissolved, we have none of this left, and it has all gone to make 0.34 moles of hydrogen ion and 0.34 moles of bromide ion. So when you put this in water, this is what you really have, 0.34 moles of the hydrogen ion and 0.34 moles of the bromide ion. So the concentration of the hydrogen ion in moles per liter is that we have 0.34 moles of hydrogen ion in 0.78 liters of solution. And so that makes 0.44 moles per liter, or 0.44 molar as the concentration of your hydrogen ion. Similarly, if you have lithium hydroxide, this actually would come as a solid. If you dissolve that in water, it's going to completely dissociate into lithium ions and hydroxide ions. So let's figure out how many moles of lithium hydroxide we're dissolving in our solution so that we can figure out how many moles of each of these ions we have. So if we have 42.70 grams of lithium hydroxide, I've just gotten the molar mass of lithium hydroxide, it's 23.95. So that is 1.783 moles of lithium hydroxide. So we are starting off with 1.783 moles of lithium hydroxide, and when it's not dissolved, we don't have any ions floating around in solution. When it does dissolve, then we have none of this left, so we have 0 of this left, and we have 1.783 moles of this lithium ion and 1.783 moles of hydroxide ion. That would make our concentration of hydroxide ion 1.426 moles per liter, or we can write this as 1.426 molar. So figuring out the concentration of hydroxide or hydrogen ions is relatively straightforward if you have a strong acid or base. Weak acids and bases are a little bit more complex because we have these equilibrium systems. These are reversible reactions. Acetic acid, as one example, when you put it into water, partially dissociates. Most of it stays together as acetic acid molecule. I think we've mentioned this before in our chapter 10. I think we did this as one of the examples. We talked about the Ka of this particular reaction, and we found out that it's mostly reactants. A small amount ends up as these ionic products. So they don't conduct electricity very well, these weak electrolytes, because if we look at the Ka values or the equilibrium constant values, they're mostly reactants, mostly the molecules. So here we have acetic acid, a proton donor. It gives a proton to water to make this hydronium ion. I believe back in chapter 10, we wrote it a little bit more simply. Back in chapter 10, we just wrote the acetic acid ionizing to give some hydrogen ion and some acetate ion. Here I've written it because you'll sometimes see the hydrogen ion attached to a water molecule to make this hydronium ion. Instead of giving up a hydrogen ion, ammonia doesn't do that. It's not an acid. It is a base, but what it can do in water is take a proton from water, making the ammonium ion and leaving some hydroxide. That would create a basic environment in your water. So the calculations for figuring out how much hydroxide, how much H+ ion you might have in the water become a little bit more complex. We're not going to deal with them right now in this course. I just wanted to ask a question, a little bit of a big picture question here. And so if we dissolve 0.25 moles of acetic acid, so if we at the start have 0.25 moles of acetic acid and we dissolve it in some water, so at the very start we don't have any of this. When it's dissolved, we still have mostly acetic acid molecules together. So unlike that previous example where we have none of this and it was all this and this, we still have a very substantial amount of the acetic acid. So we'll put 0.25 moles minus X, like some unknown amount that has dissociated, and then that amount that's dissociated we'll put here and here. So this is how we would begin to go about solving what this X concentration is. We'd first kind of start this over here. But we're not going to solve this complete equation. What we'll do is just know that our H+ concentration is not going to be 0.25. It's not going to be this high because not all of it dissolves. So what we have here is less than 0.25 moles dissolved in the 1 liter of solution. So again, we're not going to do calculations using the values of these Kas in this course, but I just did want to remind you of what they are back from chapter 10. So we have Kas for acids. Also, we didn't mention this in chapter 10, but we have Kb for base, and that is just a measurement of how much the base or the acid would make ions versus how much it stays together. So the stay together part, that's our reactants. That's going to be in the denominator. So we have acetic acid, we have methylamine here in the denominator. And then the ions that it would make, hydroxide and methylammonium ion, we have hydrogen ion and acetate ion, those concentrations would be in the numerator. So the more you make ions, the larger the numerator is going to be. So if these numbers were higher, then that means our numerators are going to be higher. And if our numerators are higher, then our Ka values are going to be higher. So the more we have the acid acting like the acid and the base acting like a base, the higher these values are going to be. So that's what this factoid is summarizing. The larger values for Ka or Kb, the more products we have. And that means we have the acid acting more acidic and the base acting more basic. So if you are comparing 2 weak acids or 2 weak bases, you can just look at their Ka values, and whichever one is larger, that's a stronger acid. If you compare 2 Kb values for bases, whichever one is larger, that's a stronger base. I did want to point out that even though we're talking about weak acids and bases as being stronger, they're not strong. So if you remember our previous example when we were talking about a strong acid, hydrochloric acid, we had all of it dissociating. We had no hydrochloric acid left. It had all become hydrogen ions and chloride ions, and we calculated that the hydrogen ion concentration was, I think, 0.44 if I remember correctly. We'll just go with that. So this does not have a Ka. If we tried to calculate a Ka value for it, we would be stuck because the concentration of HCl is 0, and we can't have a 0 in the denominator. We wouldn't be able to calculate the result. So strong acids and strong bases do not have a Ka or a Kb because Ka and Kb is just for a reversible reaction, and this reaction is not reversible. It goes all in one direction, and so we can't talk about the equilibrium constant for this. It's not an equilibrium. So if you can even see a Ka value for an acid or a Kb value for a base, you know it's a weak acid and a weak base. But you can still determine which one is stronger if you're comparing several of them. All right, so let's go ahead and use these Ka and Kb values to compare. Comparing two weak acids here. Remember, if it were a strong acid, we wouldn't even have a Ka value. So we have two weak acids, and out of these two, we want to know which one is stronger. And the stronger the acid, we're looking for a larger Ka value. We have to look at the whole number. So even though 4.3 is larger than 1.8, 1.8 times 10 to the negative 5 is a larger number than 4.3 times 10 to the negative 7. So remember to keep these exponents in mind when you're looking at these Ka values, because they can be pretty small. Most of the weak acid stays together as a molecule, we know that. So we have this as the stronger acid. For the stronger base, we have ammonia with 1.8 times 10 to the negative 5, and methylamine with 4.4 times 10 to the negative 4. So this is a larger number. If you write both of these out in regular form, if it's difficult for you to see it in scientific notation, you can try that. But this is a larger Kb value, so it is a stronger base because we have a larger Kb. I kind of skipped over this one because we had not yet taken a look at these factoids. So out of two weak acids, when you're comparing these two weak acids, whichever one is stronger, whichever one wants to give away its proton more, does not want to take it back quite as much. So it's kind of like if you have two people who are lending money, the person who is quicker to lend money, who lends money more easily, is usually not the person who is very stingy and concerned about getting it back. So if you have a generous person and a stingy person, the generous person is going to lend out money more easily, and they're not going to pester you as much about getting it back. The stingy person who doesn't really want to lend the money, they're the one who are going to start pestering you right away to get the money back. So that's what this is. If you have a generous acid giving away protons, it is not going to be very good at taking the proton back. So that's what we have here. We have a more generous acid. And so since we have this as being a more generous acid, more interested in giving away the proton, it's going to be weaker, not as strong taking it back. So the weaker of these two weak acids is going to be the stronger base. Since it's harder to get a proton away from carbonic acid and make the bicarbonate ion, it's easier for the bicarbonate ion to take back the proton. So we have the stronger of the two acids making the weaker conjugate base, and we have the weaker of the two weak acids making the stronger conjugate base. All right, I think that is where we're going to stop for this term. I'm going to stop about here, so not getting all the way through section 11.4 because we're pretty much at the end here. Since these had to do with Ka values, which we had already covered in chapter 10, I thought we could at least take a look and see how these Ka and Kb values give you an idea for how strong a weak acid could be.